So I don't want to pair this. What I'm going to do is I'm going to promote it here. And so I'm going to have one electron on hybridized P, like this. And so there are two views that I can draw for this. Okay, I can draw the top view. The top view is going to look like this. With the p orbital that's going to be perpendicular to the plane, the page, and so that would be my unhybridized p. And in each of these sp2 orbitals, I'll have a single electron. So here, here, and here. Okay, that's carbon. And then I'm going to have what next? Well, let's go with oxygen next. So oxygen is 1s2, 2s2, 2p, 4. So that's going to give us a total of 2, 4, 6, 8 total electrons. Of the 8 total electrons, 6 are valence electrons. So I have 2, 4, 6 valence electrons here. When I look at the hybridization for oxygen, what do you see as the hybridization for oxygen? And so if I want to separate these, so I have a lone pair here, and a double bond here. In order to maximize the separation between these groups of electrons, what should the angle be here? 120 degrees, which means that it can't be P. P's would be at 90 degrees, and therefore I'm going to hybridize this. I'm going to hybridize it to what hybridization? sp2 hybridization. And so 1s stays, but the valence shell, I'm going to have sp2s and 1p. So this is 2p here. And then the way I'm going to fill this depends on what I see in the Lewis structure. So I have 6 valence electrons. 1, 2, 3. Okay, where should I put the 4th? Well, it looks like the 4th I'm going to pair up. Where should I put the 5th? The 5th I'm going to pair up. Now, should the 6th one be paired also? Yeah, the 6th one I'm not going to pair up because I don't have 3 lone pairs. I only have 2 lone pairs. So I'm going to have 2 lone pairs in sp2, and that means the 6th one I'm going to put up here. Now, what I'm going to do is I'm going to change the spin orientation. I'm going to make these spin down. There's a reason I'm going to make these spin down here, and this is the reason. What's going to happen here is the oxygen is going to come in here, and sp2 is going to come in here and go spin down, and a p from oxygen is going to come over here and go spin down, and this is going to create the double bond. And so the double bond is going to look like this. An oxygen is going to come in here. Now the sp2, both of these are sp2 orbitals, but which one is bigger, a carbon sp2 or an oxygen sp2? Which one's bigger? Or are they the same size? Carbon's bigger, oxygen's smaller. Why is oxygen smaller? Yeah, higher Z. And the Z effective is going to be greater. And so let's try to draw the oxygen a little bit smaller. Oh, that works. But that's my sp2 on oxygen. So here's the sp2 on oxygens coming into the sp2 on carbon. Here. Okay, that's half my double bond. The other half of the double bond comes with a p. So I have an electron in this purple p orbital here. And then this oxygen is also going to have a p orbital here. And even though these look like they're far apart, these p's can overlap here, like this. And so that's what those lines are representing, the overlap there. And then I'm going to have an sp2 and an sp2 here. This sp2 is going to have a lone pair. This sp2 is going to have a lone pair here. And then this p here on this oxygen is going to bond with this p on this carbon here. I mean, you should have done that in a different color. And so double bond consists of what we call an sp2 sigma bond. A sigma bond is when we have the orbital overlap in the internuclear region. And then the other bond, the other half of the double bond comes from what we call a pp pi bond. And so this is an sp2 sigma. You don't need to know this for the test. And followed by pp pi bond. I'll show the pp pi bond in profile next, after we add the chlorines to this. Okay, so let me do the chlorines over here. So the chlorine is going to be 1s2, 2s2, 2p6, 3s2, 3p, 5. Now, the reason we hybridize is to minimize repulsions. Chlorine's a much bigger atom. We have the third shell now. And so the repulsions aren't going to be as great. So what some books do is they don't hybridize it. 90-degree repulsions are okay. But when do you hybridize? When don't you hybridize? And so rather than learning that, what we're going to do is we're just going to go ahead and hybridize it. So if we're going to hybridize it, we have 4 groups of electrons: lone pair, lone pair, lone pair, and bond. To maximize the separation between those 4 groups of electrons, what angle or what geometry should it adopt? Tetrahedral. And so what we're going to do is we're going to go with sp3 hybridization here. So I'm going to take my 3s and the 3p's and make 4 sp3 orbitals. But this is going to be third shell. And so these orbitals should be much bigger or much smaller. What should be happening with those orbitals? Much bigger. Correct. And then we'll just fill these here. On chlorine, we should have 3 lone pairs. So we have 3 lone pairs in sp3 and 1 single. So that's what we're going to put over here. Now these are going to be much bigger because they're third shell. So there's my sp3 with a single, except I should have written the single spin down. Because carbon's already, carbon's already spin up, sorry. So we got to make this one spin down so that they pair here. Now when we draw tetrahedral, we draw 2 in the plane. So this sp3 will be in the plane with the lone pair. And then 1 coming out of the plane. And 1 going into the plane. So this is it here so far. What I'm going to do is I'm going to rotate this molecule. So this is what I call the top view. This is looking down on the p orbitals, but what I'm going to do is I'm going to rotate it so we're looking at the side view, side on for the p orbitals. If we're looking at side view, it's going to look like this oxygen. And so I'm going to twist these sp2 so 1 sticks out. and it's going to have a lone pair, and one sticks in. This will have a lone pair. And then this sp2 will just be in the same plane. In fact, with these sigma bonds, I'll show it here. Carbon's sp2 orbital is slightly bigger. Now I'm going to look at these side views. So this sp2 is going to stick out. This sp2 is going to stick in. Okay, what this does is that it rotates the p orbitals so that they're in the plane of the page. And so here we have the p orbital on carbon, the p orbital on oxygen. Now, these are just probability boundaries, but essentially what's going to happen is we're going to get increased density in this region here. And that's what's going to create the bond. And so I wrote carbon's electrons to spin up, therefore this oxygen's got to be spin down here. And this is just one bond. And so what we have is an sp2 sigma bond, which overlaps here. And we have one p pi bond. And so the p is not a double bond because it's overlapping above and below. It's just one single bond. You have two atomic orbitals that are overlapping. Now, with sp2 sigmas, those can rotate freely without breaking the bond, but pp pi's cannot rotate. So if I left the carbon fixed and then tried to rotate the oxygen, the pp overlap will break. And therefore, the bond will break. And so sigma bonds are free to rotate, whereas pi bonds are not. And the pi bonds, again, are just, we have overlap above and below, or in front and back of the internuclear axis, whereas sigma bonds, if we draw a line between the two nuclei, the overlap is in that region. So when I look at the chlorines coming in here, the chlorines are also going to sigma bond here, except there's going to be an sp2 sigma. And so I have one electron here. And then the chlorines are going to have lone pairs in their sp3. All right, let me get rid of the dots here. Trying to show the electron cloud density. All right, so what we have here is this. This is the chlorine. And on chlorine, I'm going to have a carbon come in. And it's going to be an sp2 on carbon. It's going to bond to this orbital here. On oxygen over here, I'm going to have carbon come in. And the carbon is going to come in with an sp2 here. And a p over here. And then I erase carbons. Did I erase carbon? Yeah, I erased carbon. Let me rewrite that. Carbon is going to be sp2 hybridized. Unhybridized p and 1s here. So what we see from carbon's perspective is a chlorine sp3 is going to come in here and bond here. Another chlorine sp3 is going to come in here and bond here. And then an oxygen sp2 is going to come in here and bond here. And an oxygen p orbital is going to come in here and bond here. And so we have two single bonds to the two chlorines and one double bond to the one oxygen. All right. Did you guys get that? Yeah. Okay. So that's what you're going to do. So why don't you take a look at the next one, which is SOCl2. This is carbonyl, and then the next one is thionyl chloride, thio for sulfur. Spatially, the 3Ds are going to be closer in terms of overall. And so we go into the 3D. 4S is closer in energy, but closer in terms of geometry in 3D. You could leave that there because we'll probably talk about the expanded octet. But you should try to redraw the Lewis structure to maintain the octet. And so, so leave that, leave some extra space because I'm going to talk about that in the future. Mm-hmm. Say which orbital in hydrogen. I know it's 1s, but you should say H1s.
But next to it?
Mm-hmm. Or above it, or whatever. Okay. Okay, thank you.